with the second lecture, which is about practicalities and pitfalls. And this is, well, to some extent, this is the most boring part, things that people typically don't want to be involved with, which, because I'm a physicist, I find this actually very interesting, is about data quality, things like that. Like I just mentioned, if you don't understand something, it's actually worthwhile investigating that aspect. And so, during my early career, if you want, beginnings of my research, when I was looking into this data, I noticed things that I thought like, oh, that's weird. And they appeared to be, mostly artifacts, things that, are not genuine, but that could be attributed to poor data quality or poor data processing, all these aspects. And this is something that I've been working on quite a lot in the past. And the idea is basically, if you acquire diffusion MRI data, there's still a long journey to complete before you can actually do an analysis or to actually start addressing the cool neuroscientific questions, right? So you need to prep your data properly. Because, bleep in, bleep out. Meaning, if you acquire data, make sure you, make it as nice as possible before, doing a further analysis. Okay, so without further ado, let's continue. And I will first start with showing how a typical day at the office, pre-corona time, how that worked, okay? So this is me. I'm the physicist, crunching my numbers, doing the math, all that stuff. And this is handsome and rich Dr. Bob. And Bob steps into my office and he says like, hey, Alex, I've been collecting advanced TTI data. Can you help me with the analysis? Okay, so I'm working at a medical facility. And so there's many doctors and they're interested in this technology to use for, looking into, patients and follow-up and things like that. And so I'm like quite happy because, it's kind of my job. I help out. And so, there's more people in my lobby. Let me just admit them. There you go. Okay. And so I'm like, okay, sure, I'll help out. Sure, I can do that. And when he says that he has been collecting a lot of data, I already start dreaming like, nice quality data, happy to work with those. But in practice, I get very disappointed and even sad. As you can see, I'm crying there. And and I see that the data that he provides is kind of, ugly. And you have to be very diplomatic. So you say like, seems to be, something challenging to work with, but I'll do my best. And then even Bob brags about his data, like, there's 300s of data sets that I acquired. I'm like, I hope these data are not all like this, right? Anyways, if you look at the entire pipeline from acquiring your data, choosing some approach like DTI, and again, nowadays there's many diffusion models, and then doing, let's say, tractography, some type of analysis to get your final statistical inferences, it's a long way, right? But it's this first step, going from acquiring your data towards, basically doing an analysis and choosing your model. This step is typically neglected. Data quality assessment. When you acquire data, you need to kind of be able to assess, is the data that I acquired, good quality? Not from an acquisition point of view only, but also in terms of the processing. And this is something I will discuss in this talk, okay? Okay, so, and let me do this by showcasing, in this case, 18 different data sets. Okay, these are 18 data sets across the world. So I asked 18 centers to send me their typical data set. And by typical data set, you all know what I mean. They're probably very proud of their data, so they send even their highest quality data set. But if you just focus, and this is where our brain is brilliant, right? When we look at these images, we see patterns, we see different types of quality by just looking at these images. I mean, these are all brain images, although, if you focus on this top one over here, I mean, is this even human? I mean, it looks really, really weird, but so be it. But we all see this different patterns like the pixelation, the noise, the voxel size, bright rims, stripes, fuzziness. So you can already visually appreciate the diversity in image quality. Right? Okay, so let's focus on a few examples and see what went wrong, perhaps. Okay, so let's focus on this one. Let's zoom in. Okay, let's quickly check this. Is there anybody in the chat brave enough to state what could have been wrong here? Okay. But it's also nice to see the laughter. I can't hear you, obviously, so I'm happy to see that some people at least enjoy my lame jokes. But feel free to chat and see what's wrong. Okay, I see some like blurred, large voxels. Sure. Well, I'll tell you what is wrong with this image. Some of the slides come with a lag. Yeah, sorry about that. So I hope you can see the image now. In any case, in this case, if you focus on the color encoding, we see things being like red, green, and blue. But in this case, the color encoding convention is not as what we expect, because red should be left, right, green front, back, and blue up, down. But if you look at this, region in the centrum semiovale, the green, well, in that location, these should be, projection pathways going up, down. And if you go a bit more lateral here, you see blue, and this is in an area where you've got kind of the auditory system, like the arcuate fasciculus or the SLF, the superior longitudinal fasciculus, in that area. So green and blue are actually, well, they are interchanged. They're not, they should be swapped, right? So there has been a mix-up here. And this is something that occurred, especially in the olden days, where, conventions were not always clear, and different scanners had different headers and all these things that caused, swaps, basically changes between coordinate axes. So I'm just, swapping between left and right. I hope this lag isn't too big, but you should be able to see the same data set, but the colors blue and green basically swapped around. Okay. The good news is that nowadays this can be done automatically, like automatically detect whether you've got this swap going on. And again, it's not necessarily wrong. It's a convention. Okay, so swapping the colors, but that's a convention. However, if I now continue, you should also see like orientations of your first eigenvectors, the little discrete elements. They have a specific orientation, and like I said, this is basically because of the eigenvalue decomposition, where you do a decomposition of your diffusion tensor into its eigenvectors and eigenvalues. And the eigenvectors are basically a coordinate system in which your covariance is 0, right? That's what we've seen this morning. Well, it's a coordinate system, and maybe that coordinate system did not match the spatial coordinate system that underlies it. So you've got a diffusion coordinate system and a spatial coordinate system. And if they don't match, you'll get something like this. Notice that the color encoding is the same, but there was a flip in an axis. So the positive x-axis, for instance, became the negative x-axis. Okay. If you don't correct for that, well, you'll get something like this if you're doing tractography. Okay, the color encoding might be correct. So red, green, blue is according to convention. But if there's a flip in the sign of your first eigenvector, you'll get something like this, right? And if you just focus on a normal, so this is the same subject, same data, but just with the correct flipping of the axis, well, on the left, you don't see the cingulum bundles, for instance. These green bundles that you see on the right, on top of the corpus callosum, you don't see them. And I had this doctor who was working with the data, and he's like, Alex, look at this subject. No cingulum bundles. We should publish this in Nature. This is so unique and blah, blah. We're like, let me just have a look at the data. And I noticed this kind of axis sign flip. And I was like, okay, sorry to be a downer here, but we're not going to science. And so that was it, basically. I'm going to open, by the way, my team's questions hold on for 1 second. Because then I can see the questions on my phone while I can present, so I don't have to flick each time between the things. Okay. All right. This is so much more convenient. Okay. So there was a question, aren't people mostly using the same pipelines to extract DTIs? Yes. So meaning that, if you acquire data, you're going to assume you're acquiring the data in the same way each time, right? And then there shouldn't be any hiccups because, once you see how it should be done, should be all fine for all the other data sets. If you're doing like a multi-center study, sometimes you get data from all over the place, and these acquisitions are not always the same. And if you have a pipeline scripted to do everything automatically, because, as physicists, we're trained to be lazy, right? That's our training. You don't do any. You don't start clicking things and stuff like that. Although it is convenient, and this is what we will do with Explore DTI. Most of the stuff we do is scripting, and if you have data that is acquired with, I don't know, where the image planes are top down instead of bottom up, then there might be a flip and all these things. So that might complicate such analysis, and then you bump into these things. But also another thing is, my software was designed to work with any type of the kidney, or even non-human or non-animal, like a pineapple or other tools or other objects that you can scan. And sometimes, they're or even other scanners like Bruker scanners or scanners that don't have necessarily DICOM data. And so you get basically data from any type of machine, legacy data, where there might be these axis flips. And so, this is something to be aware of. So that's why I'm showing this maybe ad nauseum here, okay? Okay, let's move on. Okay, let's look at another example. Let's look at this guy over here. What went wrong here? Well, feel free to chat. I've got my phone here so I can look at the chat here. I was going to say borders, but okay, borders. Indeed, there's something fishy going on at the border here. This edge seems a bit bright. That's indeed a telltale sign that something might have gone wrong. Also, if you look at the genome, it looks a bit, non-symmetric, a bit fishy. Well, if we look at what the problem was, well, in this case, the subject that lied in the scanner, that subject in the scanner was not informed to lie still. So as you can see here, what I'm showing you here is this kind of movie loop of all the diffusion weighted images that were acquired, where you can clearly observe that there was subject motion, like the subject was moving his or her head. Well, actually it was me, so it's my head, his head, okay? And so if you don't correct for that, you'll get an image which looks like that on the left. If you do correct for it, and we'll come back to that later, then you can basically mitigate this aspect. So a trick here in terms of data quality assessment is just look at your data from a movie loop point of view, because you'll easily spot gross artifacts or in complications like this. But the good news is we can correct for that, okay? And another way to look at your data is to look at different views, so not just axially, but also sagittally. So to answer the comment, should we do a full pre-processing before extraction of DTI? Yes. So this is something that is important. Before you actually estimate the diffusion tensor and do all that, you need to do all these pre-processing steps. And this is something that I'll be showing you in this lecture as well. Okay? And so the first thing you do, I mean, what I do at least, is just look at the data. I mean, you can already understand so much by just looking at a movie loop and looking at your data in different views. Because in this example, well, if you look at the data axially, sure, looks good. Well, obviously, if you look at the sagittal view, you see this kind of line, which means that some axial slice was a dropout. Sure, that can happen. But if you are looking at the right, at the coronal section, you can clearly see this hyper-intense band of signals over here, right? So this is something you won't be able to spot by just looking at the axial slices, because our brain is generating an automatic windowing in terms of intensity. So if I cycle through the other slices axially, you won't spot this artifact. This subtle artifact that is easily spotted on a coronal slice, because we see the edges, we see the brightness difference between adjacent slices. Okay, so be aware of looking at your data in different ways, and that can then be feedback to your MR physicist or the MR tech operating the scan. Okay, let's look at another example. Okay, in this case, it was another center, and they sent me this data set. Let's focus on the splenium of the corpus callosum. Do we see anything abnormal here? Again, feel free to chat. If you can do this within 5 to 10 seconds, then I can see whether you have any suggestions. If not, then I can just tell it, tick-tock, tick-tock. Okay, no worries. In this case, it's really difficult to spot any artifacts, right? You just see the colorful, bright information. And indeed, difficult to spot. And to explain what was actually wrong, I'll have to take a step back. And I'm going to tell you something about physically implausible signals. In short, PIS. I realize I should have chosen the acronym more diplomatically, because I will be talking about PIS a lot now. Okay. By the way, we published this in an American journal, which is always fun, because because of their pseudo politeness, like, oh no PIS. Anyway, so it was fun to get it published in there. I mean, even the editor was like, are you sure you want to call it PIS as an acronym? I'm like, yeah, because we don't want PIS in our data. And by that, I mean physically implausible signals. Okay. I'll take you step by step through what I mean with PIS. Okay. So remember our diffusion equation, right? Our signal, or diffusion weighted signal, is an attenuated version of our non-diffusion weighted signal. Happy to see the positive reactions. Nice. So what do we know? Well, we know that our diffusion weighted signal should always be smaller than our non-diffusion weighted signal. That's how diffusion works. However, we do find regions or voxels where the diffusion weighted signal is actually larger than the non-diffusion weighted signal. And that is just physically impossible or implausible. So how is it possible then? Like how can it occur in the data? While physics and math teaches us it cannot, right? This is the equation. The equation says, mathematically or physically, diffusion weighted signal should be smaller. But in reality, if we look at the data, just looking at the numbers, we can see the opposite. Why does this occur? Well, let's now focus and put on our Sherlock Holmes hat on, magnifying glass, and look into detail in some of these areas. And looking at the same area, right? What I'm showing you now is a fractional anisotropy map in the background. So the black and white image is so the grayscale image is an FA map, and on top of that, I am showing you voxels in red that have an underlying diffusion weighted signal, which is higher than the non-diffusion weighted signal. So this is just for context, like for location. So now let's focus on a few, in this case, 4 voxels that have a clear region, like these 4 voxels, they exhibit like a non-diffusion weighted signal being smaller than a diffusion weighted signal. So let's look at the underlying diffusion data then. And let's focus on the non-diffusion weighted image. Well, what do we see? We can see in those 4 voxels that the signal is really low. And actually it's artificially low. It's an artifact causing it to be very low. And it's so low that it's even lower than the diffusion weighted signal. Hence, that's the flag we got in this map. That's why we show these kind of red voxels. We just do a logical operator on our data, like, is there any diffusion weighted signal larger than a non-diffusion weighted signal? Put it to red. There you go. Okay. And this is what we see here, something that we can acknowledge that indeed could have occurred, because in this non-diffusion weighted signal map, it's really low values. Okay. Why do we see these very low values there? Well, the artifact that is responsible for the low signal is actually related to, it bears this guy's name. By the way, I get this comment, smoothing might have solved it. Yes, indeed, in a way, because if you smooth out, you'll smooth out these low values because they're very erratic. But we'll come back to that in a moment. It's a good point. Okay, so physically implausible signals. This artifact, anybody know what the artifact is called? Well, you've got my presentation, so you go to the next slide, and then you can see this person is Josiah Gibbs. And to all the engineers and physicists and, most of you, you may have heard of Gibbs ringing. Okay, not rimming, that's something else. I made that mistake once, I'm not going to make that again. It's not rimming, it's ringing. Okay, and what you can appreciate here is what I'm showing you here with these ripples is basically, think of it as a one-dimensional signal where the vertical axis reflects signal intensity, and the and these kind of horizontal lines of this curve, they represent some signal intensity of different tissue types, right? And the artifact is related to frequency components, and we all know MRI. You probably heard of K-space in MRI, where you have to think of it as the information that we get, the radio frequencies. These are all, literally different frequency components. And if you do a Fourier transform, an inverse Fourier transform, we get our images. Okay. And if you think of Fourier transforms, you need to think of sines and cosines, and you need to think of frequency components. Well, Gibbs ringing occurs if you don't have enough bandwidth. If your bandwidth is insufficient with respect to the high frequency components. You need high frequency components to be able to capture very steep transients, like a transient between different tissue types. If you don't have those components, you'll get undershoots and overshoots in our signal, right? So these ripples here, they basically, represent imperfections in the reconstruction of our image given not enough frequency components. And if you know that, well, where do these artifacts occur most often? Well, they occur most often in regions where you have a very high signal next to a low signal, because there, there's a steep transition, and that steep transition is modeled poorly because of this insufficient bandwidth. So a limitation in the acquisition and basically the transformation of your raw K-space data into an image causes this artifact. This is a well-known artifact in MRI. And so this Gibbs ringing causes these artificial undershoots and overshoots in the different tissue types. So the dark voxels at the edge of CSF, they're artifacts. They're not genuine. And so if you then look at the corresponding estimates of your diffusivities, like fractional anisotropy, well, if you focus on it and you compare left to right, around the ventricles, you can actually appreciate they look hyper intense on the FA map. And in a way that makes sense, right? If the non-diffusion weighted signal is already low, then any subsequent diffusion weighted images, which might be higher or in the same magnitude, it suggests a lot of variation. So then you could argue, well, there's a lot of anisotropy, but it's not the case. And that's what you see here, these hyperintense regions. Okay, so if you zoom in, you clearly see the very dark areas, and they tend to correspond to kind of overshoots and undershoots, so like a dark rim next to a very hyperintense edge. Okay? All right. So, and this is kind of what I try to showcase here. You see this kind of transient between high signal, low signal, and you see this overshoot near the ventricles and an undershoot near the white matter. All right. So moving on, here's another example. And, you know, it's like once you see it, you cannot unsee it, right? If you now look at the color-encoded FA map, you can already visually see the sparks, you know, like the kind of, you know, little light bulbs appear. If you go to the middle map where you show the PIS map, you know, identify those voxels that have this undershoot-overshoot issue, and then go back to the non-diffusion weighted signal, you can actually see that, the cause of the actual artifact. Here's another example. On the left, color-encoded FA map. On the right, and then on the right, the non-diffusion weighted signal. And you can see a lot of these, you know, very dark regions near the CSF. And at some point I was like, you know, is this really an issue? But if you're comparing two groups, remember I was discussing with one of the students now about, you know, schizophrenia versus healthy controls. Well, in this case, it could be Alzheimer's versus healthy controls. And in the Alzheimer population, we know there's a lot of atrophy in the brain, meaning that there's a lot of CSF. Well, if you've got a lot of CSF, high bright regions on the non-diffusion weighted image, then you get a lot of artifacts, a lot of PIS in your data. So if you're then doing an analysis, your effect of interest might be swamped by another by this artifact, right? So you want to get rid of the artifact. And, you know, it was mentioned in the chat box, you know, smoothing might have solved it, indeed. And the trick is obviously to do this in a smart way. Because if you were to use a Gaussian, you know, filter, you're also smoothing across barriers. So your data gets an artificially, you know, degraded resolution. You'll smooth across edges. That's not good. And so what we at least thought would be an intelligent way to do is to use a kind of a total variation approach in filtering. I will skip the details. You can find it in the paper. It's basically looking at those regions which are really erratic and then correct those by doing this kind of nonlinear filter approach. So it's also a kind of smoothing that we do, but we would like to think that we're doing this in a smart way. Okay? And let me show you how it looks like before and after correcting with this technique. Well, actually, what I should have done for educational purposes is also smooth with a Gaussian filter, because then you can see the blurring effect, which we don't want. But what I'm going to show you now, before and after, is using our total variation approach. Okay, so this is before, this is after. So if you just toggle between the two images, the differences are striking. I mean, I hope you can appreciate the benefit of doing this if your data has this, you know, Gibbs ring. So as you can see, the details are preserved after the correction while minimizing the artifact. I mean, obviously, none of the techniques out there are perfect, neither are ours. So if you do correct for Gibbs ring, you know, it might not be perfect, but at least it's better than not doing anything, okay? Okay, moving on. Here's another very nice data set. Let's focus on the bottom of the brain. You see this kind of red blob here at the bottom? Well, it's, I'm gonna use a laser pointer because it just looks nicer. Anyway, here at the bottom, you can see this red patch. Okay, remember red means left, right. It's bright, so a high FA, it means like there's a high degree of structural coherence that underlies that data set. So what does it mean? Well, it means indirectly suggests that there's a direct connection going left, right in this area. Well, we're looking at the, I don't know, occipital poles roughly. Is there a direct connection between them? Not that we know of, right? So it could be an artifact. It could be a genuine hyperplasticity. Remember Russ Poldrax's brain with the, in the mid-sagittal corpus callosum area, there was also a green patch. Maybe that was an artifact. Well, I'll come back to that in a moment. But for now, we don't know anything about this dataset. Is this genuine or not? Because keep in mind, if you're a novice to the field, you just see colors and you think, oh, nice, colorful brain, must be correct, right? Well, in this case, it is not. And I'll show you how to showcase, if there's an artifact, how you can see this. And to do that, I'll need to explain something about the residuals from the model estimation. Okay, so let me start off with a quick toy example that always facilitates, the interpretation. So if I have a set of points, these yellow points, these are my measurements. And these measurements, they have an X and a Y coordinate. Okay, and let's assume my X coordinate was known. I knew what my X value was, and at that X location, I got a measurement, and this is Y. So my Y is my measurement, and my X is my predefined coordinate. Okay, if I fit a line, and this line is my model, and my model is now characterized with two parameters, the slope, A, and the offset, B. So my coefficients A and B, these are the components that I want to know. This is my model. The X values, this is my input. These are my predefined things that I know. And Y is my measurement. Well, what I can do now is I can look at my residuals. And these residuals are basically now these little white lines. These are basically indicating what is the difference between my measurement, the yellow dots, and my predictions from the model. Okay? So if I have these yellow measurements, I can actually see how far they are located from what my model, my line, would predict. All right? These are the residuals. They're the difference between what I measure and what I estimate from the model. Okay, so this is really important to understand. A residual is the difference between my measurement and what my model predicts. And keep in mind, if you have these measurements, you can estimate your model. You can fit a line through these points to actually compute A and B, right? Okay, so you've got a model, you've got measurements, you can compute A and B from these measurements. And once you've got A and B, well, you can then enter the X values to get your Y values. And if you subtract those from your measurements, then you have your residual. Okay? Well, with diffusion MRI, we've got exactly the same thing. With DTI, we have a model, or diffusion tensor. This is something we can estimate. And once you have estimated your diffusion tensor model, think of the coefficients A and B of this line. Once you have got those, you can actually enter the X value, and with diffusion tensor imaging, it would be literally entering your diffusion weighted information that you acquired, because you can now compute the diffusion weighted signal given your diffusion tensor. Yeah, I know this is a lot of information to grasp, but if you think of the diffusion tensor equation, S equals S0 e to the minus BD, well, we have our non-diffusion weighted signal, we've got the exponential, we've got B, and now we also have estimated D, or tensor. If you compute everything, we actually can end up with a diffusion weighted signal that we estimated. And so we can subtract that from our measured signal. You can do this for every voxel, for every diffusion weighted signal. If you then average those, you get a residual map. And that's what I'm showing you here. Again, it's a lot to sink in, but we're looking at a map on the right, which basically says if you subtract your measurements from what you predict given your model that you estimated, what is left over? Let's look at the perfect world. Let's assume there's no noise in our data. Let's assume our model is perfect. Then obviously our measurements are perfect, meaning that if you were to subtract them from our estimates from the model, you'll get zero, right? It's like having the equivalent would be all these points, these yellow points in this schematic would be all lying perfectly on the red line. Then all these residuals, these little white lines, they would be zero. Okay? So low values in a residual map would be good. Good quality data, good quality model. In practice, it will never be zero because of measurement noise. But the cool thing about this map is that if you look at this map and if it's uniform, meaning there's no structure in the data, it means that what you are left over with is noise. It's just measurement, thermal energy noise. And that's fine because we know all data has noise. But once you see structure in there with higher values, then you know something fishy is going on. And so when we go back to this example that I showed you with the red blob in the back of the brain, if we now look at the residual map, you see this kind of light bulb appear in that area. So in that area, we learn now from looking at this residual map that our measurements in that area are not really corresponding nicely to the predictions of our model because the residuals in that area are high. So this tells us that we have an artifact in this area. And actually, this artifact was a vibration artifact. I mean, we can talk about this later on, but it's just one of those artifacts that basically says your scanner is not good. You've got some gradients that might be miscalibrated, or something fishy is going on. Maybe some aspect of your gradient definition is wrong. So scanner is not perfect. So yeah, that's one example. Let's focus on another example. What about this guy? Well, if you look at the image, looks good. I've shown this image to experts in DJI. They could not spot an artifact. But if you look at the residual map, that's what we're going to do now. You see this bright rim across this. So the that your residual is picking up this artifact, which might not be in your way to put up your model. It's a quick way. This can be computed in seconds with your because you are your from your measurements. Is it? I mean, anyways, maybe it's a connection issue. And then there's another question. Is it possible? Anybody want to say something? Okay. I see this question. Is it possible to compare the extracted data with residual map in Explorer.TI? So yes, in Explorer.TI you can look at the residual map. So I think that answers that question, I hope. And then, can a bad model be a result of overfitting in this case? Yes, that's also a good point. You could have overfitting issues. But typically, so when I think of overfitting, that means that you might have a model with so much parameters that you could even fit the noise, right? And if you do that, the residuals will actually be really, really low. So it's kind of interesting. Overfitting will actually result in residuals that are too low. So that's an interesting question. So yes, you could have a model that is so generic that everything fits to it, like a polynomial degree function or something like that. Yeah. So that's indeed the danger, overfitting. Good point. All right. Then I'll continue. And so we were now looking, okay, so different models, bad models. We were coming back to the residuals related to this data. Remember when I showed you this data set, like, what's the green patch? Is that an artifact? Well, we can now look at the residuals in this area. And look at the residuals, right? I don't see any specific artifact because the residual map is quite uniform. In addition, the residuals are relatively low in this area. So I'm like, okay, looks good. This is a genuine underlying configuration of pathways, which for obvious reasons we did not expect because it's not very common, but it is what it is. Okay. So yeah, that was kind of a quick reassurance that what we saw in the data was genuine. And this has been observed also in a clinical setting as well. Valerina Contarino, colleague of mine, she published something about there was a child with learning disabilities, and they actually scanned regular MRIs, let's call it that, but also the diffusion data. And from the diffusion data, they noticed this kind of unconventional configuration. And obviously, it's not clear whether the cognitive disability could be attributed to this thingy, because it actually looked quite similar as this one in Russ Poldrack's brain. And trust me, Russ Poldrack, he doesn't have any cognitive issues. He's quite smart. He's there's no disability there. So it shows this shows that some configurations, while they look the same, might actually perhaps potentially result in different cognitive abilities. Another example of this, and I know there are some neuroscientists in the audience here. We were discussing callosal agenesis, so people missing a corpus callosum basically. Some people, when they have that, they have disabilities. Like, they cannot button their shirt because they need left and right motor skills to communicate with each other. But at the same time, some other people, they have incredible abilities. You may have heard the story of Kim Peek. He was also kind of the role model of this movie with Dustin Hoffman and Tom Cruise in the olden days, Rain Man. It's probably all before your time. I mean, this is a 1980s movie, so I guess most of you weren't even born. But this guy, he missed a corpus callosum, but he could learn everything. He had a photographic memory. He could play the piano once he just did it, which was kind of interesting because his hands were not connecting in a way with the motor skills. So he could do like very difficult things, which actually people with a corpus callosum have difficulty in doing because of the connections. So it's really cool stuff. But he could not button his shirt, or he had some other maybe social issues. I'm not going to say he was a social zombie, but he had difficulties communicating as far as I know. Anyway, there's a wiki page. If you just Google Kim Peek missing corpus callosum, it's fun reading about that. I see no questions. Okay, then we can continue. All right, so that was the QA. That's just quality assessment. Now we're doing some more processing stuff, things you can correct once you've figured out some of these things. And obviously they're related, right? Subject motion, I've shown you what the issue is, and now I show you how to correct for that as well, like step 2. But let's first start with, I see the link, good showing, Kim Peek, that's the guy. Anyways, correction for signal drift. And what do I mean with that? Well, if you were to acquire the same image again and again and again and again, you'll notice that the actual signal intensity is not the same. It'll drift. It will change in intensity. And most typically, you'll see that the signal will decrease. It will get lower. Why does this occur? Well, again, scanners are not perfect. They can be an enfant terrible, right? They've got character. They don't want to do what you want to do. And that's fine. And, and you try to optimize the hardware, and that's what the vendor should do. But in practice, we still see these drifts. And you may wonder, like, okay, but why would you acquire the same image again and again and again? Well, 2 things. First of all, nowadays, we don't just acquire one B0 image, one non-diffusion weighted image, but we acquire multiple ones. And this is to increase the effective signal-to-noise ratio, right? To get better quality data. Second thing I want to mention is that, indeed, we're not acquiring always the same image again, right? But we're acquiring a lot of diffusion-weighted images. And although the contrast between these diffusion-weighted images is different each time, a kind of baseline aspect to it should be the same. There should not be offsets in these images, but they're there. Okay, so if we look at the average signal of the non-diffusion weighted images, and notice on the horizontal axis, the diffusion weighted volume number can be really high. So keep in mind, nowadays we can acquire more than 100 diffusion weighted images of a single subject within 10 to 15 minutes. We can do that. And depends on the voxel size, etc., and the B value, but we can do that. And what we tend to do now is we acquire a ratio of roughly 1 to 10, 1 to 12, something like that, of number of non-diffusion weighted images versus number of diffusion weighted images. And then we acquire the non-diffusion weighted images interspersed across the data. So not just necessarily at the beginning, but throughout the kind of interspersed with all the diffusion weighted images. So we acquire a non-diffusion weighted image, and then maybe 5 diffusion weighted images, and then another non-diffusion weighted image, etc., etc. And the advantage of doing it in this way is that we can now model the imperfection of this signal drift, because we know if we acquire the same image again and again and again, like in this case showing you 7 non-diffusion weighted images or more, well, the dots at the top say what, 3, 4, 5, 6, 7, 10, 11, 12, 13 non-diffusion weighted images, we can compute a very rough estimate of the average signal in the image, right? You just compute an average value of all the non-diffusion weighted signals and you get one value. Now, if we look at the diffusion weighted signals, and these are reflected with these diamond-shaped thingies, these are all the diffusion weighted signals. By the way, you'll notice these 3 apparent rows. This is because we acquired diffusion weighted values with 3 different B values, namely 1000, 2000, 3000. And that's what you're seeing here. Remember, a higher B value allows these molecules to diffuse further and longer, meaning more diffusion. More diffusion means lower signal. And that's why you see the 3 rows. These 3 rows appear to have different signal intensities on average. Well, the lowest row is the highest B value. And Okay, so that's kind of the data that we acquired. So as you can see, a lot of data. Okay, how do we correct now for this signal drift? By the way, the signal drift is quite apparent in the non-diffusion weighted signals, right? This kind of the circles here, and this is because in those data the signal is highest, right? This is our reference, and if you go to a b-value of 1000, you can actually still see a bit of a drift. You need to kind of look a bit like this and like, oh yeah, it seems to decrease. That shows that that drift is actually also present in the diffusion weighted images. And the reason why people never saw it before or didn't pay attention to it is because in the olden days, we only acquired one non-diffusion weighted image. And when you acquire the diffusion weighted images, obviously the contrast in these images is different. So it's not really clear cut that a drift is present, because if you take the average value for each diffusion weighted signal, you'll get a different value because of the difference in contrast. But now you can see this because we acquire more data. If we acquire more data with more different diffusion weighted gradients, it takes longer. If it takes longer, you'll see the drift become more apparent. It kind of pop up more easily. Okay? So that's kind of a bit of a history there. So, okay, again, how do we correct for it? Well, in the non-diffusion weighted images, in this case, we can model with a simple low degree polynomial, maybe up to order 3. We can smoothly fit through these points the tendency of the drift. Well, if we fit this polynomial, so we now know how the drift looks like, we have characterized it with the coefficients of this polynomial, we can now detrend all the data with this information. So now what I'm showing you here, in blue is the corrected signal. So we basically multiply for each point along the horizontal axis the original data with a scale factor derived from this polynomial. And when I overlay it like this, you can actually nicely appreciate the improvement, not only in the, obviously in the non-diffusion weighted signals, the circles, right? Because now they're all at the dashed line. This is what we expect, right? If it's the same image, should be all on the line. But also the diffusion weighted images, the diamond-shaped dots, if you want, they're now more straight. They're now more on a line. Okay. Okay, great. So what do we really gain from this? Is this actually a significant improvement or not? Well, let's look at some data. Let's look, in this case, at a color-encoded FA map before correcting this artifact, before correcting for signal drift. And this is after. And you might not have seen it, so I'll toggle between them back and forward. And you might actually see this difference in intensity. And it's non-uniform, meaning that different regions have a difference in difference. Okay, so it matters. And actually, if you were to look at a histogram and look at, you know, an actual before-after subtraction of the fractional anisotropy, you'll see that the differences can be up to 10%. So it's a major improvement when correcting for signal drift. Okay. The good news is, if you don't have any signal drift in your data, then this correction strategy will be like a unity operation, right? So we always use this signal drift correction on our data, because if there's no signal drift, it will not correct for it, or not significantly correct for it. And it's really fast, because it's just fitting a low order polynomial, that's a tenth of a millisecond, and computing mean values of data, which is really fast. So it only takes a few seconds. Yeah, so somebody said like, got it, it's not a constant. Indeed, so, you know, the signal drift says like, okay, my signal is drifting, it's not constant, and it should be. It's just that scanners are not perfect. All right, going to the second one is subject motion. I'll be brief about this because we've seen, you know, the example where the subject was not lying still here. Well, you get an image reconstruction like this if you estimate the tensor. If you now were to correct for the data, you can now see a big improvement, right? So if I toggle between them, this is before correction, after correction. One thing which was typically neglected in the olden days is that, obviously, remember that diffusion contrast is orientation dependent, meaning that if your subject was lying differently oriented in the scanner, the contrast would be different. Well, if you then correct for this reorientation because of subject motion, what you should also do is correct the underlying gradient information to mimic the correct contrast after it was rotated. So this is a toy example to kind of elucidate this concept. If you have a reference image, and on the right you have your image where there was subject motion, if I were to naively reorient my image, so like register it so it's nicely aligned, I would get this. But you can appreciate that the orientation in each voxel is not pointing in the right orientation. Right? Spatially, the arrows are now in the same position. So now spatially, it's good. But from an orientation point of view, you should also reorient the B matrix. Okay, so that's subject motion, but at the same time, in the same procedure, if you want, we also tend to correct for what is called eddy currents. And this is an example where there's a very pronounced eddy current artifact. By the way, eddy is not the name of a guy. Eddies are like little swirls of vortices. They're called eddies. And so these eddy currents, they basically cause the reconstruction of the data to be not at the right position in space. So there's a k-space issue, call it that way. So the good news is, no, it's not your brain which is being stretched and skewed in the scanner. Okay, it's still safe. It's the data reconstruction part. Okay, so don't worry about that aspect. If you don't correct for these eddy currents, you'll notice a bright rim, and that's kind of a telltale sign. And it's not just within, it's not just the edge, it's also in the middle of the brain, but it's not that apparent looking at it like this. But if you correct for it, the bright rim disappears, and you could also see the improvements within the data, more within the brain. Okay, so this is without correction, with correction. Okay, so focus on any region that you're interested in, and you'll find differences in data quality. Okay, so before and after correction. Another example. Oh, I got a question. So if we do the normal movement correction before the DTI extraction, it would ruin the field direction info we need. Yes and no. You need to correct for it in the normal way, but in addition, and this is automatically done in Explore DTI, so when you correct for subject motion, Explore DTI also takes into account that the orientation information needs to be adjusted as well. So, so indeed, if you're doing this correction, you need to also correct the corresponding gradient orientations as if they were acquired along a different orientation because of the rotation. All right, the thumbs up gives the confirmation that it's clear, so I'm going to move on. Coming to what is called EPI deformation. So EPI is short for echoplanar imaging. Within MRI, it is a type of very fast acquisition, which comes with a drawback. So again, law of preservation of misery. You want to acquire data really quickly? Aha, there's a price to pay. And the price is related to what we call geometric fidelity of your data. And I'm showcasing this by this slide where I'm showing a T1 weighted image and the diffusion data. If I were to overlay the two data sets on top of each other, and let me just show this by focusing on the, in this case, gene of the corpus callosum, these data were realigned rigidly, meaning I'm just rotating and translating the diffusion data to match the T1 data. And as you can see, the data does not really match perfectly because this red part on the colored part, this is part of the corpus callosum, the genome. As you can see, it's not really nicely overlaid on the T1 corpus callosum. If I show the edge information of the diffusion data, it becomes more clear that indeed the corpus callosum seems to be stretched to the front. And not just the corpus callosum here, this genome part, but also other parts. And they're highly nonlinear, meaning if you look at the bottom of the brain, well, that actually seems to be nicely matched. If you look at the splenium of the corpus callosum, well, it seems nicely overlain. It's not perfect, but at least way better than in the front of the brain. Okay? So, what do we learn from this overlay? Well, we see that this type of deformation is nonlinear, and we also know that it is associated with field strength. So if you go to higher field strengths, then these distortions become more apparent, they become more pronounced. So, again, going to higher field strengths, great, you've got a 3 Tesla, we got a 7 Tesla, wow, great. Well, theoretically, you've got more signal-to-noise ratio. For some imaging sequences, the contrast is also more pronounced, which is great. But at the same time, for some acquisition strategies, like EPI, you'll see more artifacts. These nonlinear artifacts become more pronounced. So that's a downside. Anyway, the good news is we can also correct for that. At least we can try to correct for that. And one approach to do that is using nonlinear registration. Okay, I'll just show you a few examples before and after correction. So here's another example. In this case, this is before correction, and you can see the diffusion data, the color information, and now it seems a bit more compressed. Like if you focus on this red part here more laterally, it seems that it shifted a bit to the back of the brain. Okay, so this is without correction. If I correct for it, it looks like this. So you can appreciate, this is better. You can also appreciate the highly nonlinear aspect of it, right? So after correction, these lateral things, they shift to the front. And if you look at if you focus on the geno, it'll go to the back. See? Some parts move up, some parts move down in this image. And then people have argued, well, we know that these EPI deformations are very pronounced in areas where you have, for instance, air cavities, these big susceptibility differences between air and tissue, for instance, like the orbitofrontal cortex, what I'm showing you now. But we don't have these artifacts higher up in the cortex. That is what often is claimed, especially by those that are not correcting for this. But I'll show you an example where you can still see the benefit of correcting this. So focus now more on the cortical regions. You could argue, well, it's already nicely aligned. And indeed, some parts you may argue, well, it looks good. But there's also parts that seem to be a bit off. And I'll show you again. This is without correction, after correction. Notice the difference in quality in overlaying the diffusion data to the T1 data. And again, assuming that the T1 data has the highest geometric fidelity. And this assumption is, in my view, obviously valid because it's not using EPI, and it's a more validated sequence than, let's say, diffusion tensor imaging. But the cool thing is, you get an improvement. And it's not necessarily perfect, but at least it's better than doing nothing. Okay. Why is this important? Well, not necessarily for estimating the diffusion properties, because they stay the same. They're just located differently. But this is important for, let's say, neurosurgical planning, or if you want to use other modalities like the T1 to then capture information about the white matter. So if you're doing, let's say, using another tool, think of FreeSurfer or some other tools that can segment out different regions in the brain automatically. Well, that would be a great benefit to then look into the properties in those areas. But that assumes your diffusion data to be aligned with the T1 data. Okay? Here's another example, but then showing it from a sagittal point of view. Clearly see with and without the benefit, also the nonlinearity aspect of it. And one trick to make this work, because obviously doing a nonlinear image registration is difficult. Such an optimization requires many degrees of freedom, many parameters to be estimated. But the cool thing is we've got prior knowledge. So in this case, what we could do is constrain the degrees of freedom of our deformation field to be only along the phase encoding direction, because this is the orientation in which we know from physics where the deformations, the acquisition deformation actually occurs. So if we constrain those degrees of freedom in our optimization model, it would be a big improvement in terms of efficiency, etc., of doing this nonlinear registration. And that's what we did, and so tends to work nicely. So yeah. Okay, moving on to the last part is related to model estimation. Well, I've given you the example of a line fitting through a set of points. What if we have artifacts, like a signal dropout? Well, if we have a signal dropout, then, let's consider the red line to be our gold standard or gold truth. Well, because of the outlier now, if you use an ordinary linear least square estimation, and this is one of the many approaches to estimate something, there's weighted linear least squares, there's nonlinear least squares, there's conditional least squares, there's many estimation approaches. I mean, this is more related to statistics than anything else. But in this case, if you were to naively use an ordinary linear least squares estimation on this set of points, it will be biased towards the outlier. Okay. Most estimation approaches for a diffusion tensor, etc., especially on scanner console software, they're doing this in a really quick way, like the ordinary linear squared. It's really quick, but it's not most accurate. Again, you see it again? There's a trend going on in my talks. The conservation of misery, right? Well, you wanna know a quick result? Sure, here's the result, but it's not the best result. If you want to do it better, it takes more time, more computation time. Where does this computation time originate from then? Well, in this case, if you want to estimate this line in a robust way, any statistician will tell you, well, if you have an outlier, try to find the outlier, get rid of it, and estimate your model to the remaining set of points. And then you get a good estimate of what you need, right? And obviously for this little line and this set of points, nobody's going to hesitate to do this because it's, doesn't really matter in terms of time if it takes 1 millisecond or 10 milliseconds. But imagine that you need to do this for every voxel in your data set, right? So on average, maybe, let's say 100,000 voxels, then then maybe 1 millisecond on 100,000 voxels still will take you a minute and a half to compute, right? And in my experience, if you have this scanner console software and a medical doctor wants to look at the result, they're going to click a button and they want to see the result. And they're happy to wait either 1 second or 5 minutes to 10 minutes. Anything in between is not useful. The 5 minutes is useful because then they can get a cup of coffee or have a sandwich or something like that, come back, and then they see the result. Right? So this points to the issue of performance. And this is kind of a balance. Some people argue, well, it has to be really, really fast, etc. But I always say, go for the best option. Speed will come with age because, computers, Moore's law. Moore's law tells us that computer, they get faster, etc. every year, that doubles in performance, etc. So I wouldn't worry too much about that. If you want to do science, if you want to know your result, you want to get the most accurate result as possible, right? So be aware about which estimation approach was used to get your model results. Was there any indication that there were artifacts, like pulsation artifacts, which could have been missed, which caused, some issue? So try to make it robust, the estimation. And luckily, Explore-DTI has many options there, and one of the default estimates is a robust estimator. But we'll come back to that later. Here's just a clinical example. It was a child with a lesion, moving a lot in the scanner, lots of artifacts. This is what the scanner console software provided. This is what Explore-DTI provided, because in Explore-DTI we used the more advanced estimator. And if you toggle between them, obviously the axial slice, I kind of cherry-picked it because it was so poignant. You could really see the artifact. But also if you look at it coronally and sagittally, you can clearly see the difference and the improvement when using a robust estimator. And then finally, a few quick words on another issue called partial volume effect. I think I've mentioned it before. If you have different tissue types together, okay, let me just check how many minutes I need to talk about this. Okay, literally 5. These are the last slides. Okay. Let me share my slide again because, okay. So I assume you can see it again, right? Okay, so partial volume effect, 5 minutes, and then we can have a break. All right. So, okay, again, a bit of a story here. So when people were investigating, for instance, diffusion metrics as a function of age, they noticed big trends, like, going from 5-year-old to 20-year-old. They could see like FA values going up, for instance. And this is what you expect. You would expect microstructural organization to become more coherent, and hence the FA went up. But well, obviously, this is the critical mind of a scientist. You would say like, okay, is this really the neural substrate, which is really getting a more anisotropic behavior? Or could it be that if you have thicker bundles, because obviously if you grow some white matter bundles, they increase in volume, could it be that it's another factor that would contribute to this change in NFA values, right? Same holds for atrophy. If pathways shrink, the FA goes down. Well, what if it's driven by something else, by something we're not really interested in, like partial volume effect? Okay, so in this case, let's do a quick Gedanken experiment. Okay, let's assume a fiber bundle looks like a cylinder. Okay, that's shown on top, and it has a radius r. Well, we also know that we acquire data with voxels, where data is discrete. Every voxel has a size. And in a voxel, well, the underlying tissue, well, could potentially be multiple tissues. Like at the edge of a fiber bundle, if you draw a voxel, if you look at the voxel, it may contain gray matter or CSF in addition to the white matter. So that's what I'm trying to showcase on the bottom part. On the left, you would see a cross-section of this fiber bundle in a small fiber bundle, and on the right, there's a big fiber bundle. And in light gray, I'm showing you voxels where there's a clear partial volume effect between two tissue types. Let's call it CSF and white matter. Let's focus on the singlet bundles, for instance, right? They're adjacent to CSF. Well, in those light gray voxels, we can imagine that we have a lower FA value there because there's also CSF in there, and CSF has low FA values. So if you have a mixture of CSF and white matter, in those voxels, you would assume that the FA is lower compared to the middle part. And this middle part in dark gray, let's assume we've got pure white matter there. So the FA value is high. If you were to do an analysis and you want to compute the FA of a fiber bundle, of the entire bundle, or even a part of a fiber bundle, in that region, the FA is then computed as the average value of all the FA values in these voxels, for instance. Well, you can imagine that for smaller fiber bundles with a smaller diameter, the contribution of the partial volume affected voxels to the entire estimate of FA is larger than the larger fiber bundles, because the contribution scales like circumference versus surface, which is proportional to the radius divided by radius squared, right? Because we know the circumference of a circle is 2πr, and the surface is like πr squared, something like that. Okay, but in any case, it scales with 1 over r. So the bigger the radius, the smaller the effect of partial volume affected voxels. Well, if that effect is smaller, then the contribution of low FA values will be smaller, so the actual result will give you a larger FA value. Okay, we put this to the test, so we were just curious, like, can we actually see this? And so what we did was we used our virtual scissors. We looked at the cross-section, in this case again, of the singlet bundle. And indeed, you can already see the partial volume effect occur. You see the edge has lower FA values than the middle. This is what you kind of expect. And then what we did was we just plotted the thickness of these fiber bundles and correlated them with the FA. So the FA value, as you can see, was highly correlated with the thickness. So the thicker the fiber bundle, the higher the FA. And by the way, every dot in this scatter plot is a different subject. And we each time cut the cingulum bundle in the mid-coronal section, right? So where this kind of scissors is shown. So we do this for many subjects. And then to our amazement, we actually saw, well, what we predicted, what was actually verified here. So we were like, at one point we were really happy because we thought like, what we guessed happened. But at the same time, it brought a lot of concern because think of all these studies showcasing that the FA as a microstructural measure, well, it could have been all due to morphological aspects with partial voluming. Well, while the majority of the variance in this experiment was explained by just the size of the fiber bundle, luckily, many people have looked into similar trends with aging and FA by also taking into account volume of these pathways as a covariant node of interest. And luckily, there was still correlation. There were still associations. So on the one hand, indeed, FA seems to be confounded by partial volume effect. On the other hand, FA is still a metric of underlying microstructural organization. So that's the good news. Let's see, any questions? No. Okay, good. Well, and then I think we're at the end of the second talk. Any questions? And just wondering, I guess you guys are getting hungry, right? But that's fine. So we have a break now. I mean, we can. What we could do is after the lunch break, we continue with the third lecture. Then I guess. To be honest, I'm already getting hungry myself as well. So. Okay. Cool. Yeah. So what shall we do? I mean, we'll reconvene maybe in maybe an hour or half an hour, or I don't know how long you would need, but let's make it a proper break so people can relax a bit as well, right? Yeah, sure. Yeah. Well, so so one version requires MATLAB. So when you see the P code version, I call it the MATLAB version, that requires you to actually have a MATLAB installed with some of the toolboxes. And then if you go into MATLAB, you just type in main explore DTI. Obviously, you need to browse to the folder in which explore DTI then is kind of unzipped, because you'll see all these different folders. And then there's one file called main explore DTI. And if you type in main explore DTI in the MATLAB command prompt, it should start. But for the other ones, if you don't have MATLAB installed on your computer, well, you'll need to you need to basically install the MATLAB runtime component libraries first, and then you can basically run the main explore DTI file. But this is something I'm happy to go over this at the beginning of the session, right? What would be convenient, obviously, is if you could already download all the files, because that can take a while, and if you can already install the MATLAB component runtime library. So if you're working on a Mac, make sure you, when you go to the website of MATLAB, use the 2000, and I think it was, let me just double check, the 2000, no, yeah, the 2020A version. So release 2020A. Let me just go to the chat. Okay, so again, if you don't have MATLAB, first go to this link. Okay, if you go to that website, let's see, I think I've, let me try that again. I don't think okay. Let's see. So there's a question. The question is, it should be 2020A. Okay, and you have three choices basically. You've got Windows, Linux, or Mac. If you click on those links, you'll notice that it's a big file. It can take a while to download. Okay, so it's good that you try that, or try to do it now because it can take a long time to download. And then you need to install this file. That can also take a few minutes. Okay, and be patient there. So if you're using a Windows and you double click to install, if it doesn't pop up immediately, this MATLAB runtime library, just wait for a second because it's a big file. It needs to kind of extract itself, and it takes a while. By the way, I'm going to mute everybody because some people are using their mics. So once you've got that one installed for your operating system, then the second step will be to basically unzip the link to the Explore DTI file. So that's specifically, one of the three links that I sent you. So let me just quickly chat that as well. So there's, that's one of these three, depending on which operating system you have. But there's a question. So we should get MATLAB and the P code version, right? Well, so what I've explained now is what I call the standalone version. That means that you don't have the MATLAB software, like the license to code in it. So what I've been telling you now was to download the MATLAB runtime compiler. It's like, think of it as a kind of platform to be able to run Explore DTI. So it's kind of using the free downloadable libraries to then run Explore DTI. The P code version, the MATLAB version, that's only if you have a software license. So if you have got MATLAB running and you're scripting yourself in MATLAB, and it's like a program language, MATLAB. And then you could use the other one, the one that I also put in the link. So let me do that again. So if I then copy, paste. So if you have MATLAB installed, and by that I mean the actual software tool, where you have a license, where you actually pay for. And maybe student versions are free, but they might not have all the toolboxes in there. Because if you want to use Explore DTI in MATLAB, like natively in MATLAB, then you need to also have specific toolboxes like image processing, statistics toolbox, things like that. I hope that makes sense. If not, I can explain again, let's say after we had some more food, then we can think more clearly. Any questions now? Any burning questions? And again, if you don't know, what I'm talking about, then I suggest you just download the MATLAB runtime component library and the Explore DTI one for your operating system. I think that's what you can do already. And then, I'll take you by the hand and I'll show you what to do to install it. But okay, I'm even happy then to say to you, like, share your screen and show me what you're doing, and I can help out like that. But I am also aware that there's 40 plus participants, and logistically ideally, things like installing software, we should do this beforehand. And that's why I envisage in our practical session later on that I'll be showing like demo style. I'll be doing it, and then obviously you can try if you've got the software running, and I can answer some questions. But yeah, I think we'll do it like that, and maybe in an hour or something like that, I'll ask you, who of you has been already able to download and install the software successfully. Then I got an idea of where we are. All right. So it's 10 to 12 in an hour. Let's round it up to, in my time, 1 p.m. And then I'll see you again for the third lecture then. All right? But the newer versions of MATLAB also work. Yes, but the MATLAB versions, meaning the actual MATLAB software, not the standalone version. So if you want to use the standalone versions, you need the 2020A runtime libraries, because then otherwise it doesn't match, because the standalone versions I compiled, these are compiled with that version, 2020A. So hopefully that makes sense. All right, I'll see you in an hour and 10 minutes. Bye-bye.